LU factorization with row permutation. Previously, we performed a simplified LU factorization, but the question is, when does that process fail? There are two cases. Case 1, when C becomes an entire column of zeros. The solution to this case is relatively easy. Generally, at the kth step, if the C vector becomes a column of all zeros, we set the kth entry to 1 and define R as usual. Case 2. In this case, we need row permutations. And this is the case where C is not all zeros, but the pivot value is 0. Remember, we divide C at each step by pivot, so pivot cannot be 0. It turns out, all we need to do is to permute rows of the current temp matrix and the corresponding rows in L. Let's look into an example. We will use Julia to calculate LU factorization, so we won't do it by hand. Here we have a matrix M, and we would like to compute LU factorization. We use linear algebra package. We define our matrix M, and here I am calling LU function and storing the results in variable f. Notice that f is a structure. It has different fields. We have L, f.L, U, and P. L is the lower triangular matrix, U is the upper triangular matrix, and P is the permutation matrix. In general, we have P times M equals LU. And we can verify that L times U equals P times M in the last line. So we see L is a lower triangular matrix, U is an upper triangular matrix, and P is our permutation matrix. So we just learned a more general case for the LU factorization, meaning P times A equals LU. Now we want to see how we can solve the system of linear equations A times X equals B. So all we need to do, we start from AX equals B. We multiply both sides by P from the left. This way, we recognize that P times A is LU. So what we get is LUX equals P times B. Notice that the right hand side now is a new vector P times B and not just B. So we define a new variable Y to be U times X. Therefore we get Ly equals P times B and U times X equals Y. We first solve for Y via forward substitution because L is a lower triangular matrix. Given Y, we solve for X via back substitution because U is an upper triangular matrix. Let's look into an example. Here we have a system of linear equations with 4 variables. We define our matrix of coefficients A, the right hand side B. We compute the LU factorization of A and store it in variable f. In this line, we solve for Y. The notation backslash means L inverse times P times B. This will give us Y. However, we do not want to explicitly invert L, and this notation will perform forward substitution for us. It's a smart operator and it will recognize the structure of the problem automatically. Next time, given y, we want to solve for x. Again, we use the backslash operator, and this means x equals u inverse times y. But again, the backslash operator will not explicitly invert u. To test if x is the solution indeed, we can calculate a times x minus b. And we see that up to the machine precision for float 64 numbers, the difference is effectively 0. In the next chapter, we're going to look into the determinant of the product, matrix inverses, and matrix transpose.